Welcome everyone to the sixth and final video here on chemical kinetics. Or in this video, we're going to talk about catalysts. Okay. So a catalyst, right? Now that we've talked about collision theory and activation energy and the temperature dependency rate and things like that, we can start talking about catalysts. Okay, because how a catalyst works is it speeds up your reaction by providing an alternate pathway with a lower activation energy. Okay. Right, so in this plot here, right, our catalyst, right, takes our activation energy, which initially, right, was all the way up here, right, and now it reduces it to some new activation energy, right, which is much lower, right, which if I have a lower activation energy, that means more molecules have enough energy to overcome that barrier and form products, okay? Catalyst will not affect the reactants or the products of your reaction, right? So it does not affect, say, the enthalpy change. It doesn't make something exothermic or endothermic or things like that. It does not impact that whatsoever. It only affects how quickly a reaction occurs. Okay? So again, if we think about lowering the activation barrier, right, for a given chemical reaction, right, I have more molecules now with the amount of energy required to overcome that activation barrier and form products, so my reaction is going to happen faster. Okay, right? There are two types of catalysts that one deals with. There are homogeneous catalysts, right? Catalysts that are in the same phase of your reactants. Enzymes are examples of these things, right? So biochemistry, your body uses catalysts all the time to speed up a chemical reaction. And it does so using enzymes, which are dissolved in solution, just like the reactants are. Okay, and then there are heterogeneous catalysts, right, where the phase of the catalyst is different from that of the reactants. Okay, and a typical example of this is the catalytic converter in your car. Okay, so the most common example of heterogeneous catalysts are solid metals that catalyze gas phase reactions. Okay, and how those typically work, right, is what happens are your molecules come to the surface of your catalyst and they bind to the surface, and often when they bind to the surface, for example, these hydrogens, it could potentially break the hydrogen bond. So now you have these kind of lone hydrogens bound to the surface of this catalyst, and so now this other molecule can come in, right, and react with the hydrogens bound to the surface, right, as it gets bound to the surface, and eventually leave, right, with more hydrogens on it than where it started, right? And so the catalyst, right, essentially, in this example, right, helps reduce the energy barrier required to, say, break those hydrogen-hydrogen bonds before you have to form the hydrogen-carbon bonds in this chemical reaction, okay? Right, catalyst in the reaction mechanism, right, will appear first as a reactant and then as a product, okay? Catalysts, right, during the mechanism are consumed, but then they're produced again later on, okay? In the overall chemical reaction, catalysts will not appear, okay? Because they are not a reactant, they are not a product, right? But they will appear in our mechanism. But again, catalysts are consumed and then produced later, okay? Right, intermediates, as we talked about, are produced and then consumed, while catalysts are consumed and produced. But neither of these things appear in the overall chemical reaction mechanism. Or sorry, in the overall chemical reaction. They will appear in the mechanism, but not the overall chemical reaction. All right, so an example here of, say, a catalyst, right? Right, so, right, freons, which were used in a lot of aerosol sprays, right, damage the ozone layer by introducing chlorine atoms into the atmosphere. Those chlorine atoms catalyze this reaction, right? Ozone is O3, okay? So catalyze this reaction where O3 plus O forms O2, okay? And it does so through this mechanism where chlorine atom binds with O3 to form ClO plus O2. That ClO then goes on to react with an oxygen atom to form Cl and O2. Okay. Notice here that the chlorine is consumed and then produced. Okay. So when this overall reaction takes place, right? The concentration of chlorine does not change, okay? This is a catalyst, right? Chlorine here is our catalyst, right? But notice here that ClO is produced and then consumed in the reaction mechanism, right? ClO here, right? This is an intermediate, right? Right. So our ClO here is our intermediate, okay? While Cl here is a catalyst. Okay. Another example, right, is say the decomposition of H2O2, right? So hydrogen peroxide can decompose into water and O2 naturally by itself, but if I introduce bromine ions here, okay, I can undergo this chemical reaction, right, where bromine acts as a catalyst because bromine is consumed in the first step and then produced later on in the second step, okay? And then again, our intermediate here is Br2, which is produced and then consumed later, okay? So, right, the overall mechanism, right, the reaction, how it worked, right? So my initial reaction, right, the uncatalyzed reaction has some large activation barrier here. Well, my catalyzed reaction is broken up into two steps, each with their own activation barrier, right? But these activation barriers are smaller than the uncatalyzed reaction, right? Which makes the reaction go much faster, okay? So that is another example of catalysts, right? And so that wraps it up for chemical kinetics, where we've talked about what is the average rate of reaction, rate laws, integrated rate laws, reaction mechanisms, right, collision theory, and catalysts. Okay.